Hello everyone, welcome to this video class where I'm going to explain a single tone amplitude modulation. Now here the meaning of single tone is that means we are considering only one tone in the message spectrum. So one tone here means one single frequency. So in the last video, if you observed my video, I have considered the entire spectrum of an audio band, and after modulation, how this low pass signal is actually translated into a band pass signal with occupying a certain bandwidth. Okay, so where I considered the entire the audio band of say 0 to some wHz, the highest frequency assumed as wHz. But in this video, I'm going to explain considering a single frequency in the message spectrum. That single frequency is FM Hertz. Let us consider. Okay, that FM Hertz can be say 1 kilohertz, 5 kilohertz, within the again range of that audio band of 20 hertz to 20 kilohertz. Now, see, so I consider one again my message signal here. Message signal m of t is equal to am cos 2 pi fmt, where fm is a single tone message frequency. Okay. Now we consider again sinusoidal carrier wave. Mathematically, it is represented something like this. That is c of t is equal to ac cos 2 pi fct. Now the conventional AM or a standard equation for AM, that is double sideband full carrier, is given by this. That is s of t is equal to 1 plus mu cos 2 pi fmt cos 2 pi fct, where this mu is nothing but it is a modulation index which is given by ka am. Okay, that ka am is am is a peak amplitude of the message signal, and ka is nothing but it is the amplitude sensitivity parameter. Okay, so that directly I have taken that particular the term mu actually over here in this case. Okay, so this is mu is a modulation index. Now when I multiply this signal, okay, so when I multiply this components over here, and I'll get two terms, that is AC cos 2 pi fct from the first one. The second term is mu into AC cos 2 pi fmt and cos 2 pi fct. Again, I apply a trigonometric rule of cos A cos B, considering this as A and this as B. Okay, so I will get this equation finally for a standard AM or a conventional AM signal, that is double sideband full carrier, where this particular component is nothing but it's a unmodulated carrier, as you are aware. The second part is nothing but it represents actually the upper sideband with the frequency of fc plus fm with the amplitude equal to mu ac by 2. The third component is nothing but it is the lower sideband, okay, fc minus fm hertz with the amplitude again same as the amplitude of the upper sideband. Now what I will do over here is, okay, I want to represent this in the frequency domain by using a frequency spectrum, both mathematically as well as graphically using a spectrum. So what I'll do is I'll take a Fourier transform to this particular equation directly. Okay, so I have a three cos signals. As you can observe over there, I have a first cos signal unmodulated carrier, second cos signal with a frequency of fc plus fm and mu ac by 2, the third cos signal that is fc minus fm hertz and with the amplitude of mu ac by 2. So I have a three components. If I take a Fourier transform to individually to these three components by using this relationship, okay, I can represent this cos signal as half of exponential j 2 pi fct plus exponential minus j 2 pi fct. Okay, this exponential term, when I take a Fourier transform to exponential term in the frequency domain, it is delta function shifted by fc. That is delta f of f minus fc for this, and delta of f minus fc for this particular exponential term. So by using the same relationship and applying to all the three components, I will get this equation. That is, from the first term, I'll get half of AC delta of f minus fc plus delta of f plus fc. Again, this is a cos signal over here, so I get a mu AC by 2, that is mu AC by 4. Okay, this is a cos signal with the frequency component of this, so I should get a delta functions over there, that is delta of f minus fc minus fm plus delta of f plus fc plus fm. Similarly, for the third component, I'll get this delta function. So what I have actually over here is, in the frequency domain, I have three set of delta functions, okay, for each individual cos signals. Now the next task is to represent this in the frequency domain. Now in the frequency domain, okay, I have taken this again same equation over here for a reference purpose. Now this is the single tone signal, okay, this is the message signal with the frequency of fm hertz. Okay, so if I represent that in the frequency domain, message signal, this will be like a delta function because it's simple cos signal, correct? I have taken a single signal here. not the entire spectrum. So I can say that my m of t is nothing but it is cos 2 pi fct with the amplitude equal to am. So m of t is actually equal to am, okay, this is am cos 2 pi fmt. So frequency, single tone frequency is FM hertz here. I have not considered the entire spectrum. So give me a second. FMT. So this is the single tone frequency over here. So I have not considered the entire spectrum as I did in the previous video. So that 20 hertz to 20 kilohertz or the entire bandwidth of say W hertz here, right? Highest frequency of W hertz. So in the previous case, if you observe my previous video, though this entire spectrum was actually shifted by FC hertz after modulation, we get a band pass signal. But here I have considered only FM. So that is single frequency. If I take a Fourier transform to this particular equation, that is for a message signal, again I should get a delta function according to the same rule which we applied over here. I should get a delta function at minus FM and plus FM. That's what I represented. Okay. So again, a cos signal is nothing but it is AC cos 2 pi fct. Again, you take a Fourier transform to this. I should get two delta functions at minus FC and plus FC, right? But FC is always more than FM, so that's why I represented somewhere here. Okay. Now coming to this equation, so I should have what exactly the meaning of this is from the first part. So we should have a delta function at the minus FC, so this one, okay, and this is another delta function on the minus FC. This is plus FC and minus FC. That is this term and this term. And the second case is okay. So the second part is there's a delta function at minus of FC plus FM. Okay, minus of FC plus FM. So I should have a delta function set FC plus FM. This one, okay, this one, this delta function. Just give me a second. Missed it. Okay. Now, so I should have a delta function somewhere here. Okay, another delta function somewhere here. Mirror image. From the third equation again, I should have a two delta functions. So this one and say this one. Okay. So these are the delta functions which are represented. So if I consider only the single tone or single frequency in the message spectrum, this is what actually I will get in the frequency domain. So both represented time domain as well as frequency domain in this particular representation. Okay. So this is nothing but a single tone modulation of amplitude modulation, I can say. Okay. Thank you. Thank you for watching.